Folks, hello and welcome to your midweek bonus for, topic number 5. This is problem 1031, which is one of the network models out of this homework section. The thing that you probably say right away when you look at how I have presented this Excel spreadsheet is you're going to say that this looks a little bit different setup-wise than what we've seen since week 3 when we started looking at network models. And it is based on the information that's presented and how we are going to go about solving this. And I think once I get through with some of this discussion here, you'll see that it is advantageous to set this model up this way. And one of the things that we've talked about from the beginning here is, there's obviously some science that goes along with linear programming. But when it comes to solving these models, there's probably more art to setting up the spreadsheets than there is science. And there is no right or wrong way to do that. But what there is, where you get the advantage is from a visual standpoint, from a scalability standpoint, and from something that makes sense to you that you can use to describe to, if it's somebody that you're working with or whatever, something that you can use and you can explain a problem and how you've modeled it in Excel if you get to that point. And so what we have done here, again, is slightly different, but I hope as I read through this and I explain what's going on here in order to solve this, that this setup over here will make sense. So the problem reads, a long-distance telephone company uses a fiber optic network to transmit phone calls and other information between locations. Calls are carried through cable lines and switching nodes. A portion of the company's transmission network is shown here. The numbers above each arc show the capacity in thousands of messages that can be transmitted over that branch of the network. To keep up with the volume of information transmitted between origin and destination points, use the network to determine the maximum number of messages that may be sent from a city located at node 1 to a city located at node 7. And so, the way that we pass information these days, I think this probably makes sense. So just to point out here, there are 7 nodes, 1, 2, 3, 4, 5, 6, 7, and it looks like in order to pass from node 1 to node 7, which is one city to another, there is possible routing. You could probably almost look at this almost like a cell phone network. So there's a number of there's a different number of, or a different quantity of messages that can be sent over each one of these arcs. And remember that these are in thousands. And so the idea here is, how do we maximize the flow from 1 to 7 going through 2, 3, 4, 5, and 6 with these maximums. One of the challenges here, and if you've read this section of the reading for the week, there's this idea of balance of flow in a network model like this, which is to say, in order to make this work from a modeling standpoint, how many ever messages we're able to transmit through this network. What we're going to do is we want this circular relationship, or this balance of flow, such that whatever we push from 1 to 7, we want to return that same number of messages to number 1. And that way, this kind of works and helps us in the modeling aspects to make sure that, number 1, that all messages, obviously we don't want drop messages, so the maximum number is moved, and then they are effectively re-ingested here at number 1 to come up with this idea of balance of flow. So what I have set up over here is basically, I have translated this model into arcs, start points, and end points in the capacity of each. So I'm not going to go through the whole thing here, but let me just take, for example, line 5 here. So the start node 1 and node 2, the capacity as shown here is 4,000 messages. So that will take you all the way down to row 16. And as I just discussed, what we're going to do here in order to maintain this balance of flow is whatever I have moved to node 7, I am going to return that to node 1 here. So this is almost like a dummy relationship in order to make sure that we execute this balance of flow idea. The decision variables are actually going to be in column D, and it's going to be the number of messages shipped from 1 to 2, 1 to 3, so on and so forth. Let's see. So I think that covers this. Again, I just wanted to make sure I explained what was going on here. Again, from 7 to 1, just to return the number of messages that made it to 7 back to 1 for balance of flow. And this is the idea of balance of flow. So at node 1, we are going to talk about number of units that come into node 1 and number of units that come out of node 1. And if you look here, this dummy variable here, once we actually get down here, I think what you're going to find is that the optimal solution will show up in this cell right here. But then we're going to move these, again, move these messages through the network. So whatever we end up moving to 7 will come up here and start in node 1. And this is actually where the balance of flow works out. So whatever comes into 1, that will also go out of 1. So the messages that come out of node 1 are in cells D5, D6, and D7. So whatever the sum of these decision variables are will be the output of node 1. And then for node 2, let's see, so what we should see here is, let's see, D8 and D9, that's what we should see here, D8 and D9. What comes out of 3 is, let's see, D10, 11, and 12 that you see here. Out of node 4 should be D13 and D14, which you see. Let's see, out of 5 should be, looks like just D15. Out of 6, D16. And then out of, let's see, out of node 7 is going to be this value D17. Again, this is kind of your dummy relationship. Now, this net shipment, the in or the out minus the in, or the in minus out, however you want to look at that, that must be equal to 0. And again, that is to ensure this balance of flow. And what we do here, in order to make sure that happens, we put another column over here for the supply. We set these values all equal to 0. And then you'll see a constraint in the model that says the net shipment must be equal to the supply. And that ensures our balance of flow. So I think that is the setup. Let's see, let's go to solver here. And I think I actually already have the setup for you. The objective cell is I18. And if you look at this cell, I don't want to click on it because I don't want to mess this up. But actually, this cell is set equal to whatever I produce in cell D17. And I will show you that here in just a minute when I solve the model. And obviously, we want to, the optimization here is to maximize the number of messages that we ship through from city, whatever's represented at city 1 to city 7. And remember, the decision variables are D5 through D17. We show that here. Let's see, there are 2 constraints here. D5 through D16, which is here, actually here, D5 through D16. That must be less than or equal to the capacity at each or on each arc. That is this first constraint. So the unit ship can be no more than the capacity that can be handled from node, in this case, 1 to 2. And then the balance of flow, remember, let's see, the out minus the in, that difference must be 0. And so we set that cell in each case equal to this supply cell, which is strictly a hard number 0. And I think, let's see, I think we got simplex LP. Let's solve this and see what we come up with. And it looks like, let's see, 10, and that is, I believe, in thousands. Let me just check here. In thousands, yes. So it looks like the maximum number of messages that can flow through this network is going to be 10,000. And remember, I think I said, yeah, that objective cell is set strictly to sell whatever we come up with in D17, which again is that kind of that dummy relationship to take whatever we put or whatever we move to city 2, I guess, that's located here at node 7. And that way, again, that we keep the model churning and maintain the balance of flow. Notice in all cases here, what comes into 10 goes out of, or what comes into 1 goes out of 1. Whatever comes into 2 goes out of 2. Whatever comes into 3 goes out of 3, so on and so forth. So I think that relationship makes sense. Let's see what else. Yeah, only a couple constraints here. Again, the maximum number of messages that can be shipped from the start node to the end node. And let's see, in all cases here, less than or equal to. Yes, let's see, some loss capacity here, some loss capacity here, and I think that's it. So you'll notice that not all of these lines are used up, and that's based on probably what happens somewhere downstream. You can go through that and convince yourself of what that looks like. So I will, let's see, I will post a video for this. I will also post this Excel file so that you are clear on the relationships within the model and then within the solver itself. So I hope this one is helpful. If there's any discussion we need to have, don't be afraid to post a question on the class questions board, and we will do that. Take care and enjoy the rest of your week.